SuperSharp is aiming to capture ultra-high resolution thermal images of the Earth, and it's aiming to do this using a revolutionary technology of unfolding space telescopes that can actually fit in the size of a microwave.
Thermal imaging captures a temperature map. It tells you exactly where any energy is being used, because whenever we use energy, it ends up as heat. And so we're able to see that from space and map it on a global scale. For example, we can see which buildings are leaking the most heat and therefore need retrofitting. Or we can look at which power stations are operating based off the heat coming out of those facilities, and start to understand the energy use at a global scale, which is going to be really important to tackling climate change and monitoring energy use.
So the name of the telescope is Hibiscus, and it's Hibiscus because you have 5 petals when it's deployed, and Hibiscus is a 5-petal flower.
The technology behind the telescope is a real combination of technologies. So we've got state-of-the-art robotics in the unfolding mechanisms, but the really key part of the technology is that once the telescope is unfolded, all of the optics have to be aligned to better than 100th the width of a human hair.
The unfolding self-alignment technology works in a combination with extremely high precision mirror actuators, and then also a metrology system which allows us to reflect light off of the primary mirrors, measure it with the metrology system, and create a feedback loop where mirror actuators can use nanometer precision to precisely align the mirrors to each other and the other optical surfaces present in the telescope.
And that's a real differentiator, because it means that we can unfold the optics, which means they can be much lighter weight for launch, and they can still be much bigger when you get into space and capture the really high resolution images you need.
The space environment is challenged because we have thermal cycles, so your structure is always changing because of thermal. You have radiation in space, so you need to make sure all the components they resist that, and of course we have the launch.
I believe some of the biggest challenges are the fact that we need to think on a scale of nanometers in terms of the level of precision that Hibiscus needs to unfold once it's in space, and it really changes things in levels of precision from what most engineers, and certainly in my background, I've been used to.
We first came across maxon through, I guess it was kind of the obvious design choice from one of our senior mechanical engineers when he was first prototyping some of the unfolding mechanisms, because of the quality and the robustness, and the fact that maxon have got real experience in using these sorts of motors in space applications as well.
Maxon's been providing products into space applications for over 25 years now. We've developed a wealth of experience in understanding our products and what modifications need to be done to survive in the environment.
Maxon motors are used for all the deployment mechanisms for the Hibiscus telescope. So it's used to move the telescope arms up and down, they're lead screw driven, and it's also used for the deployment in conjunction with some worm gears in order to deploy the petal mechanisms.
Working with SuperSharp, we went down the road of using the DCX motors, the brushed DCX motors, with GPX gearboxes.
Maxon's products have been really important in the design of our deployment mechanisms, because we know that they're highly reliable, high quality motors, and that Maxon have got great experience of how to use these motors in challenging environments like space.
It costs a lot of money per kilogram to send product into space. So Maxon's power dense motors, being small and efficient, is a good starting point for any space application.
Maxon offers a huge amount of customization, which as an engineer is great for myself, but also their technical knowledge as well really helps you dial in just precisely what you need. And for us that's been amazing, so we can spec exactly what motor we'd want, make sure that the current and the voltages we're running at are perfect, then exactly the gearboxes we'd like as well, and then with the encoders that we need for the level of precision that we want.
SuperSharp's got some really exciting future plans. In the next couple of years we plan to launch our first satellite and to demonstrate the unfolding self-aligning technology in space, and from there grow and manufacture more telescopes and satellites to build constellations, so that we can really understand the Earth at wavelengths that we've never really imaged it in that sort of detail before.